A few years ago, scientists pointed their telescopes at a small red star just 35 light-years away from Earth. What seemed to be an ordinary star, nothing special about it, ended up revealing an entire system of hidden planets. These worlds are rocky like Earth and orbit very close to their star, in orbit so fast that one year there lasts only a few days here. One of these planets might even have water, the most important ingredient for life as we know it. This discovery made scientists ask a mind-blowing question. Could we be looking at a place where life might have started, so close to us in the universe? Get ready to fall asleep while listening to this video and travel through this mysterious star system. Subscribe to the channel, leave your like and comment where in the world you're watching from. Get comfortable and relax. Let's begin. Imagine a star so common that it makes up the vast majority of suns in our galaxy, yet so faint you could never see it with your naked eye. This is the reality of L98-59, a red dwarf star that's quietly hosting one of the most intriguing planetary systems we've found in our cosmic neighbourhood. Let's talk about this stellar host itself, because understanding the star is the absolute key to unlocking the secrets of the worlds that orbit it. L98-59 is what astronomers classify as an M3 dwarf star. That string of letters and numbers places it firmly within the category of red dwarfs, which are by far the most populous type of star in the Milky Way. Think about it this way. For every star like our Sun, there are at least 10 of these smaller, cooler, redder stars. They're the silent majority of the galaxy's stellar population. This particular one is located about 35 light-years away from us, in the direction of the southern constellation Volans, which is Latin for flying fish. In the grand scheme of our galaxy, that's right next door, making it an exceptionally convenient target for detailed study. Now, what does being a red dwarf actually mean for its physical characteristics? First and foremost, it is small and lightweight. L98-59 has roughly 1/4 the mass of our Sun and about 1/4 its radius as well. This compact size leads directly to its other defining trait. It is much cooler and dimmer. Its surface temperature is thousands of degrees cooler than the Sun's, which shifts the bulk of its energy output into the infrared part of the spectrum. To human eyes, it would appear a dim, ruddy hue if you could see it at all. This low luminosity has a profound effect on its planetary system, squeezing what we consider the habitable zone, the region where liquid water could exist incredibly close to the star. But the most mind-bending property of red dwarfs like L98-59 isn't just their abundance, it's their longevity. While a star like our Sun has a total lifespan of around 10 billion years, a red dwarf burns its nuclear fuel at such a miserly, slow rate that it can keep shining for not just billions, but trillions of years. That is an almost incomprehensible stretch of time, far longer than the current age of the universe. This extraordinary stability offers a potentially enormous window for the development of chemistry and possibly biology on any suitable planets in orbit. A star system with that much time on its hands is a fascinating thought experiment for life's potential. However, the story of a young red dwarf is not one of tranquil stability. There is a significant catch, and it revolves around the star's magnetic activity. Red dwarfs are notorious for being magnetically hyperactive, especially in their youth. L98-59 is estimated to be a few billion years old, which for a red dwarf still counts as relatively young and potentially spry. This activity manifests as frequent and powerful stellar flares. These are sudden, violent eruptions on the star's surface that blast out torrents of high-energy radiation, including ultraviolet light and X-rays, along with streams of charged particles. For any planets huddled close to the star to stay warm, this creates a punishing environment. Imagine a world being repeatedly scoured by radiation baths that can strip away atmospheres and sterilize surfaces. This is the central paradox and the central question for systems like L98-59. Can planets nestled in the cozy habitable zone of such a star survive its fiery tantrums long enough for life to take hold, or are they doomed to be barren, irradiated rocks? That's why studying the host star itself is so critical. By measuring its flare activity, its rotation, and its X-ray output, astronomers are not just studying a star. They are diagnosing the environmental context for its entire planetary family. The planets are products of their star, shaped by its light, its gravity, and its temper. L98-59 serves as an almost perfect laboratory for this investigation, because of its proximity and its system of transiting planets. When we look at it, we're looking at a template for the most common type of planetary system. If such a star survive its fiery tantrums long enough for life to take hold, or are they doomed to be barren, irradiated rocks? That's why studying the host star itself is so critical. By measuring its flare activity, its rotation, and its X-ray output, astronomers are not just studying a star. They are diagnosing the environmental context for its entire planetary family. The planets are products of their star, shaped by its light, its gravity, and its temper. L98-59 serves as an almost perfect laboratory for this investigation because of its proximity and its system of transiting planets. When we look at it, we're looking at a template for the most common type of planetary system in the galaxy. Every piece of data we gather from it helps refine our models for thousands of other red dwarf systems we've discovered. We learn what's typical and what's unusual. For instance, how does its activity level compare to other M dwarfs of similar age? Does it have star spots that cause subtle brightness variations? Or of any planet, potentially making it very different from Earth. So when we characterize L98-59, we are doing more than just cataloguing another star. We are building the foundational profile needed to interpret every future observation of its planets. The star's spectrum tells us its chemical composition, which mirrors the primordial soup from which its planets formed. Its stability over observational timescales allows for the ultra-precise measurements needed to detect the tiny wobbles caused by planetary gravitational tugs. Its size, precisely measured, is the ruler we use to measure the size of the planets when they transit. In essence, the star is the stage, the lighting director, and a sometimes unpredictable character in the drama of its planetary system. Without a deep understanding of this red dwarf, any talk about oceans or atmospheres on its planets is just speculation. With a growing understanding, we can start to ask sharper, more informed questions. The recent discovery of potential water worlds in this system, for example, becomes infinitely more compelling when framed against the behaviour of the star. Could a thick atmosphere protect a planet from flares? Could a global ocean redistribute heat from a permanent day side to a permanent night side? These are stellar questions as much as they are planetary ones. That's the enduring importance of focusing on the host. As new telescopes like the James Webb Space Telescope turn their gaze towards this system, they will be looking at the star just as much as they look at the planets. They will watch for the minute dimming as a planet passes in front, and they will dissect the starlight that filters through a planet's atmosphere, if one exists. But that starlight itself carries the imprint of the star's nature. Disentangling the stellar activity signals from the planetary atmospheric signals is one of the biggest technical challenges in exoplanet science today. L98-59, being relatively quiet for its type and so close by, provides one of the cleanest possible setups for this delicate work. In the end, L98-59 is a profoundly ordinary star by galactic standards, and that is precisely what makes it so extraordinarily valuable. Its commonplace nature means that the lessons we learn here are broadly applicable. If we can understand how planets form, evolve, and perhaps even retain habitability around this typical red dwarf, we will have made a giant leap in understanding the cosmic story of planets and life. It is a humble, small red sun, but it illuminates some of the biggest questions we can ask. Every measurement of its flickers and flares, every calculation of its lifespan and luminosity adds a crucial piece to the puzzle. The planets may be the flashy discovery, the new worlds that capture our imagination, but they are born from and bound to their star. So, as we continue to explore this compact system 35 light-years away, we must always start with the star. This long-lived, faintly glowing and temperamental red dwarf that holds the entire story in its gravitational embrace. Its properties set the rules of the game for every process that occurs within its sphere of influence. From the violent processes of planetary formation billions of years ago, to the subtle chemistry in a potential ocean today, the shadow of the host star is long and defining. That's why astronomers dedicate so much time to studying stars like L98-59. They are the anchors of their systems, the prime movers, and the ultimate arbiters of fate for the worlds that circle them. This particular anchor, being so close and so well positioned for observation, offers us a front-row seat to the most common type of cosmic drama in the galaxy, and that is an opportunity we cannot afford to miss. So we have this fascinating star, L98-59, with its potential for hosting intriguing worlds, But this immediately leads to a very practical question. How do we actually find asterisk planets orbiting a distant, faint pinprick of light 35 light-years away? We can't see them directly, they're utterly lost in the glare of their star. The answer is a brilliant blend of patience, precision technology and inference. Astronomers don't see these worlds in the traditional sense. They deduce their presence by watching for the tiny telltale effects they have on their host star. Two primary methods have revealed the secrets of L98-59 and thousands of other systems, the transit method and the radial velocity method. Think of it like detective work where the star is your witness, and you're looking for the subtle signs that something is tugging on it or passing in front of it. The star's light is the key piece of evidence. The first and most prolific tool in this detective kit for finding exoplanets, especially for a mission like TESS, is the transit method. The concept is beautifully simple in theory, but mind-bogglingly difficult in practice. If a planet's orbit is aligned just right from our vantage point on Earth, it will periodically pass directly in front of its star, blocking a tiny fraction of the star's light. This event is called a transit. For a star like our Sun, an Earth-sized planet blocks about 0.00084% of the light. That's like watching a gnat fly across a car's headlight from miles away. For a smaller red dwarf like L98-59, the same sized planet blocks a larger relative fraction, making the dips slightly easier to detect, but it's still an extraordinarily subtle signal. This is where spacecraft like NASA's Transiting Exoplanet Survey Satellite, or TESS, come in. Launched in 2018, TESS is designed to do one thing incredibly well: stare at vast patches of the sky for months at a time, measuring the brightness of hundreds of thousands of stars with phenomenal stability, looking for those periodic, repeating dips. It found L98-59's planets by noticing that the star's light very precisely dimmed by a fraction of a percent at regular intervals. The depth of the dip tells you the size of the planet relative to the star. A bigger planet blocks more light. The timing of the dips gives you the planet's orbital period, its year. From test data, scientists initially saw 3 distinct periodic dips, revealing 3 worlds with orbits of 2.25 days, 3.7 days, and 7.45 days. But the transit method, while powerful, has a limitation. It only gives you the planet's radius. You know how big it is, but you have no idea how massive it is. This is where spacecraft like NASA's Transiting Exoplanet Survey Satellite, or TESS, come in. Launched in 2018, TESS is designed to do one thing incredibly well: stare at vast patches of the sky for months at a time, measuring the brightness of hundreds of thousands of stars with phenomenal stability, looking for those periodic, repeating dips. It found L98-59's planets by noticing that the star's light very precisely dimmed by a fraction of a percent at regular intervals. The depth of the dip tells you the size of the planet relative to the star. A bigger planet blocks more light. The timing of the dips gives you the planet's orbital period, its year. From test data, scientists initially saw 3 distinct periodic dips, revealing 3 worlds with orbits of 2.25 days, 3.7 days, and 7.45 days. But the transit method, while powerful, has a limitation. It only gives you the planet's radius. You know how big it is, but you have no idea how massive it is. This is where spacecraft like NASA's Transiting Exoplanet Survey Satellite, or TESS, come in. Launched in 2018, TESS is designed to do one thing incredibly well: stare at vast patches of the sky for months at a time, measuring the brightness of hundreds of thousands of stars with phenomenal stability, looking for those periodic, repeating dips. It found L98-59's planets by noticing that the star's light very precisely dimmed by a fraction of a percent at regular intervals. The depth of the dip tells you the size of the planet relative to the star. A bigger planet blocks more light. The timing of the dips gives you the planet's orbital period, its year. From test data, scientists initially saw 3 distinct periodic dips, revealing 3 worlds with orbits of 2.25 days, 3.7 days, and 7.45 days. But the transit method, while powerful, has a limitation. It only gives you the planet's radius. You know how big it is, but you have no idea how massive it is. A physical world with known size, mass, density and orbit, The discovery of the fourth planet, L98-59e, and hints of a fifth showcase the power of combining these methods over long observation campaigns. The transit hint from test data was confirmed and its mass pinned down by painstaking radial velocity work. It's also important to understand what these methods cannot tell us from this data alone. A transit doesn't automatically show an atmosphere, though it can hint at one if the dimming has a specific shape. Radial velocity gives a minimum mass because the orbital tilt is unknown. The true mass could be higher if the system is tilted relative to our line of sight. But for compact flat systems like this one, the minimum mass is often very close to the true mass. These detection techniques also explain why we find so many hot planets close to their stars. A close-in planet transits more often, giving more signal, and creates a stronger gravitational wobble, making it easier to find. It's a selection bias. These are the low-hanging fruit. The planets in the L98-59 system, crammed inside the equivalent of Mercury's orbit, are perfect examples of this bias. They are not necessarily the most common type of planet, but they are the most common type of planet asterisk we can currently detect asterisk with these methods around faint stars. Future technologies aim to change that. The quest to move from detection to true characterization, to studying the atmospheres and surfaces of these worlds, relies on a more advanced use of the transit method. During a transit, a tiny fraction of the star's light filters through the planet's atmosphere, if it has one. Different molecules in the atmosphere absorb specific colours of this starlight. By comparing the star's spectrum when the planet is in front of it to the spectrum when the planet is beside it, astronomers can theoretically tease out the atmosphere's chemical fingerprint. This is called transmission spectroscopy, and it is the primary hope for the James Webb Space Telescope. For a star as small and cool as L98-59, the signal from a transiting Earth-sized planet is relatively larger, making it a prime target. But again, it's a monumental challenge, requiring many transits to build up a clean signal. The radial velocity method also continues to advance. Next-generation spectrographs are pushing towards even finer precision, aiming to detect the wobble caused by Earth-mass planets in more temperate orbits. This could reveal planets in the system that don't transit, completing the family portrait. So, when you hear about a discovery like the L98-59 worlds, remember the incredible indirect chain of logic behind it. It's not a photograph. It's years of data collection, the meticulous pixel-by-pixel photometry from a space telescope, and the night after night of spectral measurements from a mountaintop in Chile. It's algorithms sifting through noise to find a repeating pattern, and teams of scientists modelling gravitational interactions. These methods have moved us from wondering if other planets exist, cataloguing thousands, and now to the brink of asking what their air is made of. Behind it, it's not a photograph, it's years of data collection, the meticulous pixel-by-pixel photometry from a space telescope, and the night after night of spectral measurements from a mountaintop in Chile. It's algorithms sifting through noise to find a repeating pattern, and teams of scientists modelling gravitational interactions. These methods have moved us from wondering if other planets exist, cataloguing thousands, and now to the brink of asking what their air is made of. They turned starlight, the most basic astronomical data, into a rich source of information about unseen companions. The story of discovering exoplanets is ultimately a story of measuring vanishingly small effects, a flicker of light, a shift in colour, and having the audacity to interpret those effects as entirely new worlds. Every time a planet transits L98-59, it creates a signal that travels through space for 35 years before our telescopes catch it. We are, in a very real sense, reading a message sent by the system itself written in shadows and wobbles, and slowly decoding its meaning to reveal a complex planetary architecture that, in a very real sense, reading a message sent by the system itself written in shadows and wobbles, and slowly decoding its meaning to reveal a complex planetary architecture that, just a few decades ago, we could only imagine. This indirect detection is the foundation upon which all our knowledge of exoplanets is built, and it continues to be the workhorse driving the field forward, revealing systems that constantly challenge and refine our understanding of how planets form, and what kinds of environments are possible around the galaxy's most common stars. The methods are a testament to human ingenuity, allowing us to perceive the imperceptible and map the unseen, building a census of worlds one tiny, precise measurement at a time. From a single point of light, we extract orbits, masses, densities, and soon atmospheric compositions, painting a picture of distant solar systems that continues to be the workhorse driving the field forward, revealing systems that constantly challenge and refine our understanding of how planets form and what kinds of environments are possible around the galaxy's most common stars. The methods are a testament to human ingenuity, allowing us to perceive the imperceptible and map the unseen, building a census of worlds one tiny, precise measurement at a time. From a single point of light, we extract orbits, masses, densities, and soon atmospheric compositions, painting a picture of distant solar systems from the subtle whispers of their starlight. Now that we've seen how astronomers spotted these worlds through their subtle effects on starlight, let's zoom in on the first one they found, the closest planet to the star. This world, known as L98-59b, is the system's innermost child, and it sets the stage for understanding the extreme equilibrium temperature for this planet, which is a basic calculation of how warm it is based on its distance from the star and the star's brightness, is somewhere in the range of 500 to 600 degrees Fahrenheit. That's hundreds of degrees above the boiling point of water. It is a profoundly hot world, a roasted sphere of rock. But the temperature is just the start of the story. Being so close, the planet is almost certainly tidally locked. This means the same hemisphere permanently faces the star in a condition of eternal scorching daylight, while the opposite hemisphere is trapped in endless frigid night. The terminator line between these two extremes would be a place of perpetual twilight, but even there the conditions would be severe. The atmospheric dynamics, if any atmosphere exists at all, would be wildly different from anything on Earth, potentially funneling insane winds from the hot side to the cold side. However, the biggest question mark hanging over L98-59b is the very existence of an atmosphere. This is where its location becomes a brutal liability. Red dwarf stars, especially in their youth, are notoriously active, prone to frequent and powerful flares of ultraviolet and X-ray radiation. A planet sitting this close is bathing in that high-energy radiation bath constantly. For any primordial atmosphere that might have formed when the planet was young, this would have been a death sentence. The process is called atmospheric erosion. High-energy photons from the star slam into molecules in the upper atmosphere, giving them enough energy to escape the planet's gravity entirely. Over millions and billions of years, a steady stellar wind can strip away an atmosphere layer by layer, leaving behind a bare, desiccated rock. For L98-59b, the radiation flux is so intense that most models suggest it is extremely unlikely to have retained a substantial atmosphere. It might possess a tenuous exosphere, a few scattered atoms clinging to the surface, or perhaps outgassing from a still molten interior could provide a transient thin shroud, but nothing resembling the thick protective blankets we see on Earth, Venus, or Mars. This likely airless state makes it a very different kind of rocky planet. Without an atmosphere, there is no weather, no erosion in the traditional sense, no protection from stellar radiation and micrometeorites. Its surface would be directly exposed to the vacuum of space and the full glare of its red sun. The day side would be a searing landscape, perhaps with pools of molten metal or rock if the temperature is high enough, while the night side would be one of the coldest places in the system, possibly cold enough to trap volatile ices in permanent shadow. It is a world of extremes, a study in contrast forged by gravity and fire. So why is this apparently hellish, uninhabitable world so important to astronomers? Precisely because it represents a baseline, a control experiment. L98-59b shows us the end result of what happens to a rocky planet that forms too close to an active red dwarf. By studying it, we learn about the processes of atmospheric loss. When we look at its slightly more distant siblings, like Planet C and especially Planet E in the habitable zone, we can ask crucial comparative questions. Why did this one lose its air while another might have kept it? How much does initial composition, or the presence of a magnetic field, matter? This planet is a laboratory for understanding the limits of atmospheric survival. Future observations, particularly with the James Webb Space Telescope, might still attempt to probe for any trace of an atmosphere. If against the odds, Webb detects even a thin one, it would revolutionize our models. It would mean that some rocky worlds are far more resilient than we thought, or that geological processes can replenish an atmosphere faster than a star can strip it away. A non-detection, on the other hand, would powerfully confirm our theories about stellar erosion. Every measurement of this hot super-Earth provides context for the entire system. Its density tells us about its internal composition, likely a mix of rock and iron, perhaps with a large metallic core. Its precise orbit helps model the gravitational interactions that might have shaped the system's architecture during formation. It is the anchor point, the innermost known member of this compact family. Understanding its stark reality also helps temper our expectations when we hear about Earth-sized planets. Size alone does not make a world Earth-like. L98-59b is a stark reminder that location is everything. It is a testament to the diversity of planetary outcomes, formed from similar materials as Earth, under the same star, yet its destiny was radically different due to a simple accident of distance. It is a celestial example of nature's forge, creating not just habitable paradises but also sterile, broiled stones. For anyone dreaming of alien landscapes, this world's imagined vista is one of dramatic, silent desolation. The dayside sky would be dominated by a huge, dull red orb, perhaps filling a significant portion of the heavens, blotting out the stars. The surface, if solid, could be cracked and volcanic, or smoothed by ancient lava flows. There would be no blue sky, no soft light, just the relentless glow of the nearby star. It is a vision of a planet pushed to its physical limits, a warning about the dangers of getting too close to a temperamental sun. Yet, within that warning lies immense scientific value. By cataloguing worlds like L98-59b, we begin to map the boundaries of planetary science. We learn what combinations of star, planet and orbit lead to bare rock, and which combinations might allow for more clement conditions. This particular world, as the closest in, also experiences the strongest tidal forces from the star, which could keep its interior hot and geologically active for longer than a similar world farther out. This internal heat might drive volcanism, which could, in a cruel twist, contribute to that thin, transient atmosphere through outgassing, only for the star to immediately blow it away. It's a dynamic, if brutal, cycle. In the grand narrative of the L98-59 system, Planet B is the opening chapter, establishing the harsh ground rules imposed by the star. It shows us the starting line for planetary evolution in such an environment. As we move outward through the system, we will see how slightly more distance changes the story, potentially allowing for atmospheres to cling on, for temperatures to moderate, and for the possibility of liquid water to emerge. Blow it away. It's a dynamic, if brutal, cycle. In the grand narrative of the L98-59 system, Planet B is the opening chapter, establishing the harsh ground rules imposed by the star. It shows us the starting line for planetary evolution in such an environment. As we move outward through the system, we will see how slightly more distance changes the story, potentially allowing for atmospheres to cling on, for temperatures to moderate, and for the possibility of liquid water to emerge. But that story only has meaning because we have this first data point, this scorched sentinel standing guard at the gates of its star. Its very existence, and our ability to measure its properties so precisely from 35 light years away, is a triumph of modern astronomy. It may not be a world we would ever want to visit, likely airless reality of being too close, then its neighbour L98-59c presents a far more nuanced and tantalising picture. This is the middle child of the originally discovered trio, and it occupies a fascinating and precarious position that has astronomers leaning in with intense curiosity. Let's talk about what we know. This planet is slightly larger than Planet B, with a radius about 1.35 times that of Earth and a mass around 2.22 times our planet's. It's still very much a rocky super-Earth, but it's got a bit more heft. Its orbit takes 3.7 days, which still feels impossibly fast by our standards. But that extra distance from the star compared to Planet B makes all the difference in the world. That distance places it in a very special astronomical zone. L98-59c sits right on the inner edge of what's termed the optimistic habitable zone for its star. This is a critical concept to unpack. The habitable zone is not a fixed, perfectly defined region. It's more of a fuzzy band where conditions might allow for liquid water on a planet's surface. The conservative habitable zone is a narrower, more restrictive definition that requires more ideal conditions. The optimistic zone extends further in, including planets that could potentially harbor liquid water if they have just the right kind of atmosphere to compensate for the extra stellar heat. Planet C is in that optimistic borderland, is not squarely in the comfortable middle, it's on the hot inner rim. This makes it a transitional world, a test case for how much punishment a planet can take and still hold on to the ingredients for habitability. The central burning question for L98-59c is the same one we asked for Planet B, but with a much more uncertain answer. Does it have an atmosphere? Here the models clash, and the possibilities are wide open. It is far enough from the star that the blistering radiation and stellar wind might not have been completely stripping. It may have had a better chance to form and retain a substantial gaseous envelope during this system's early chaotic days. But might and may are the operative words. Its fate hinges on a delicate balance of factors we're still trying to measure. Did it start with a thick, Venus-like atmosphere of carbon dioxide? Does it have a protective global magnetic field to deflect charged particles from the star? How active was L98-59 in its wild youth, and how much atmosphere was boiled away in that period? We simply don't know yet. This uncertainty is what makes the planet so compelling. It represents a real fork in the road of planetary evolution. One path leads to a world that is still a hellscape, just a slightly cooler one than its inner sibling. Without a significant atmosphere, or with a thin, transparent one, L98-59c would be a bare, tidally locked rock. Its dayside would be brutally hot, though not as hot as Planet B's, and its nightside would be deeply frozen. Any water would long since have been lost to space, or be trapped as ice in permanent cold traps on the night side. It would be a sterile, intermediate world, showcasing a step in the atmospheric erosion process. The other path, however, is far more interesting. Suppose L98-59c managed to hold onto a dense atmosphere. In that case, everything changes. A thick shroud of gases, particularly greenhouse gases like carbon dioxide or water vapour, could work to redistribute heat around the planet. On a tidally locked world, this is the key to potentially moderate conditions. The atmosphere could carry warmth from the permanent day side over to the night side, preventing the far side from becoming utterly frigid and potentially allowing for a wider range of surface temperatures. A sufficiently dense atmosphere could also create enough surface pressure to allow liquid water to exist, even if the average temperature is higher than Earth's. It could rain, it could have weather systems, it might even have regions, particularly in the twilight terminator zone or at higher elevations, where temperatures are stable enough for liquid water pools. This is not to say it would be Earth-like. It could be a superheated high-pressure steam bath, more akin to a prehistoric Venus, but it would be a world with an active climate and chemistry, a world with complexity. This is the razor's edge it lives on. The difference between a barren rock and a dynamic shrouded world comes down to the composition and thickness of its air. This is why L98-59c is such a high priority target for atmospheric characterization with the James Webb Space Telescope. Webb has the capability to analyse the starlight filtering through the planet's limb during a transit. If it detects molecules like carbon dioxide, water vapour or methane, it will be a monumental discovery. It would tell us that rocky worlds in this volatile region around red dwarfs can indeed cling to atmospheres. The specific mix of gases would then tell a story about the planet's geology, its possible volcanic activity, and even hint at geochemical cycles. And non-detection, while less flashy, would also be incredibly informative. It would suggest that the inner edge of the habitable zone around active stars is indeed a desert, that the stripping power of the star is too great for planets this close to build a stable climate. It would push the likely boundary for habitable conditions further out, perhaps to where Planet E resides. Beyond just the atmosphere, the planet's tidal locking presents another layer of climatic possibility. The permanent day-night configuration could lead to extreme weather patterns, like ferocious supersonic winds roaring from the hot side to the cold side if an atmosphere exists. Cloud formation might be bizarre and localised, perhaps with permanent cyclone-like storms at the substellar point, the point directly under the star, or vast ice sheets on the dark side. It's a climate modeller's dream and nightmare simultaneously, a scenario with no direct analogue in our solar system. Understanding L98-59c is also understanding the concept of the runaway greenhouse effect at close range. Is it possible that this world once had oceans that boiled away, leaving a thick, steamy atmosphere that then itself was eroded? Or did it always be a dry world, devoid of significant water from the beginning? Its density gives clues about its bulk composition, hinting at how much water and other volatiles it might have incorporated during formation. It's a puzzle where every piece of data, from its mass and radius to a future atmospheric spectrum, helps constrain the possible narratives. In the grand architecture of the system, Planet C also plays a gravitational role. Its interactions with its siblings, particularly Planet B and the outer planet D, help stabilise their orbits and tell us about the system's dynamical history. It is a crucial link in the chain. For anyone following the search for habitable worlds, L98-59c is a masterclass in cautious optimism. It teaches us that not every planet in the habitable zone is habitable, and that the zone itself is a starting point for discussion, not a guarantee. It embodies the transition from the clearly uninhabitable to the potentially habitable. Its study forces us to refine our definitions and our models. It's a reminder that habitability is not a binary yes or no switch, but a complex, multi-dimensional spectrum of conditions. This middle world, with its 3.7-day year and its position on the edge, is therefore one of the most important targets we have for understanding the diversity of terrestrial planet outcomes. It represents a plausible, and perhaps common, intermediate state between the hells and the havens. By unravelling its story, we don't just learn about one planet, we learn about the fate of countless similar worlds orbiting the most numerous stars in the galaxy. It is a stepping stone both in space and in our scientific understanding, leading us from the fire of Planet B toward the deeper mysteries of the outer, cooler worlds in this remarkable nearby system. Every observation dedicated to this specific planet is an investment in a broader cosmic census, helping us predict what we might find when we point our telescopes at other faint red dots in the sky. Its very ambiguity is its greatest gift to science, pushing our technology and our theories to their limits as we strive to answer a deceptively simple question: what is the true nature of the world in the middle? Building on that uncertainty, on that fascinating maybe of Planet C, the story of the L98-59 system took a dramatic and unexpected turn. The initial 3-planet discovery was impressive enough, but as astronomers continued to sift through the data with ever more sophisticated tools, they found something that truly rewrote the system's importance. Hidden in the subtle patterns of starlight and stellar wobble was a 4th world, and this one changed everything. This planet, named L98-59e, is not just another rocky blob, it is the crown jewel of the system, a world that catapulted L98-59 from being an interesting case study to one of the most compelling targets in the search for life beyond our solar system. The discovery itself is a testament to modern astronomical prowess. It wasn't found by a lone telescope in a single eureka moment, but through persistent collaborative analysis of data from both TESS and the Espresso spectrograph on the Very Large Telescope. The planet's signal was weaker, its transit shallower and less frequent, and its gravitational tug on the star more subtle than its inner siblings. Teasing out its signature required ruling out other possibilities, like stellar activity mimics, and building a solid statistical case. What emerged from this painstaking work was a planet with an orbit of about 12.8 days. That number, 12.8 days, is the key to its revolutionary status. That orbital period places L98-59e squarely within the star's conservative habitable zone. This is the more restrictive Goldilocks region, where, given an Earth-like atmosphere and sufficient water, liquid water could stably exist on a planet's surface. Unlike Planet C on the optimistic edge, Planet E is in the comfortable middle. It is far enough from the star to potentially avoid the worst of the atmospheric stripping, yet close enough to be warmed by its faint red sun. It is the first planet in this system discovered to be unambiguously in the prime real estate for life as we understand it. But the surprises didn't stop with its location. By combining its transit depth, which gives radius, with its radial velocity signal, which gives mass, astronomers could calculate its density. And here is where things get incredibly interesting. The density of L98-59e is lower than that of a purely rocky world like Earth. The numbers suggest that a significant portion of its mass is incredibly interesting. The density of L98-59e is lower than that of a purely rocky world like Earth. The numbers suggest that a significant portion of its mass, perhaps up to 30%, could be composed of water. This doesn't necessarily mean it has a surface ocean you could sail on. The water could be mixed into the mantle or exist in a subsurface layer. But the leading and most thrilling interpretation is that L98-59e is a bona fide water world or ocean world. Picture a planet with a rocky core, enveloped by a deep global ocean hundreds of kilometers deep, topped with a dense atmosphere. It would be a planet with no land masses, no continents, just a boundless aquatic expanse under an alien sky. This possibility fundamentally alters how we view this system. We are no longer just looking at a series of increasingly cooler rocks, a subsurface layer, but the leading and most thrilling interpretation is that L98-59e is a bona fide water world or ocean world. Picture a planet with a rocky core, enveloped by a deep global ocean hundreds of kilometers deep, topped with a dense atmosphere. It would be a planet with no land masses, no continents, just a boundless aquatic expanse under an alien sky. This possibility fundamentally alters how we view this system. We are no longer just looking at a series of increasingly cooler rocks. We are looking at a system that likely has a world with the key ingredient for life, in the right place, and in staggering abundance. The implications for habitability are profound, but also complex. An ocean world offers a stable global environment. Water is a superb solvent, facilitating the complex chemistry that leads to life. Limit the geochemical cycling of nutrients that many think is vital for sustaining life over geologic timescales. Furthermore, without a silicate weathering cycle from continents, the planet's long-term climate regulation through processes like the carbonate-silicate cycle might be different or less effective, potentially making its climate less stable over billions of years. The planet's tidal locking is another major factor. If one hemisphere permanently faces the star, the eternal dayside ocean would be constantly heated, while the nightside ocean could potentially freeze over, creating a global ice cap over the liquid water beneath. The atmosphere would have to work extremely hard to transport heat from the dayside to the nightside to prevent this. Alternatively, if the ocean is deep and dynamic enough, ocean currents could perform this heat redistribution, creating a more uniform global temperature. The climate of such a locked water world is something climate modelers are only beginning to simulate. Another critical question is the atmosphere itself. Does 98-59e have one? Given its greater distance and lower equilibrium temperature, it had a much better chance of retaining volatiles than planets B or C. The water we suspect it has could be in the form of vapour in a thick, steamy atmosphere. Detecting that atmosphere is the next great hurdle, and the James Webb Space Telescope is poised to try. The transmission spectrum of this planet would be one of the most sought-after datasets in exoplanet science. The discovery of water vapour in its atmosphere would be a landmark achievement, confirming the presence of the molecule in the habitable zone of a nearby star. Beyond water, scientists will look for other gases like carbon dioxide, methane and oxygen. While oxygen could be a sign of life, on a world like this, it could also be produced abiotically through photochemical processes, so its detection would require careful interpretation. The mere existence of L98-59e also hints at the system's formation history. How did a world so rich in water form so close to its star? Traditional thinking suggested that the inner regions of planet forming disks around red dwarfs might be too hot for water ice to condense, leading to dry, rocky planets. Water would then be delivered later by icy comets from the outer system. But a 98-59e suggests another possibility, that the building blocks of planets in the inner disk could have been rich in water from the start, perhaps locked up in hydrated minerals or as part of larger water-bearing planetesimals that migrated inward. This challenges and enriches our models of planet formation around the most common stars. In the broader context of exoplanet exploration, L98-59e stands as a beacon. It is one of the closest, smallest and most characterizable habitable zone planets we know of that transits its star. That transit is everything. It gives us a geometrical alignment that allows for atmospheric studies. There are other potentially habitable planets, like those in the TRAPPIST-1 system, but L98-59e, around a brighter and slightly more stable star, offers a cleaner, clearer signal for our telescopes. It is a prime target not just for JWST, but for the next generation of giant ground-based telescopes like the Extremely Large Telescope, and future space missions like the Habitable Worlds Observatory. It represents a pathway from discovery to true characterization. The journey from seeing a dip in starlight to potentially identifying the chemical makeup of a temperate world's atmosphere is being paved right here with this planet. It transforms the abstract concept of a habitable zone of planet into a tangible data-rich object of study. The revolutionary discovery of L98-59 teaches us a humbling and exciting lesson. Our first look at a system is often incomplete. There are frequently more worlds waiting to be found, and sometimes the most important one is hiding in the noise, requiring patience and ingenuity to reveal. This planet elevates its entire stellar family, making L98-59 a system we will be studying for decades to come, a cornerstone in our quest to understand if we are alone in the universe. It is no longer just an example of a compact red dwarf system. It is a destination, a place where our imagination and our science converge on the profound possibility of another living world, orbiting a silent red sun just 35 light-years away. The discovery of a potential ocean world like L98-59 nestled in its star's habitable zone is the kind of moment that redefines a system's importance. But to truly understand what that means, to grasp the real chances of habitability on such a world, we have to deeply examine the nature of that habitable zone itself. The concept isn't a one-size-fits-all template. It is a dynamic and often harsh reality that is completely dictated by the star at the centre. For a red dwarf like L98-59, the habitable zone is a profoundly different environment compared to the one we enjoy around our Sun. This difference isn't just academic, it directly controls the fate of any planet found within it, turning the simple idea of liquid water possible into a complex engineering challenge for nature. Let's break down why. The primary overwhelming factor is the star's low luminosity. L98-59 is a dim bulb compared to our Sun, outputting only a tiny fraction of the energy. For a planet to receive enough warmth to possibly have liquid water, it has to huddle incredibly close. Think of standing by a small campfire versus a roaring bonfire. To feel the heat from the campfire, you need to be right next to it. This is exactly the situation for planets in a red dwarf's habitable zone. In our solar system, Earth orbits at a comfortable distance, taking 1 year to go around. In the L98-59 system, the habitable zone is compressed into a region so close that a year lasts mere days. L98-59e, the promising ocean world, has a year of just 12.8 days. This extreme proximity comes with a cascade of consequences that shape every aspect of planetary science and potential biology there. The first major consequence is tidal locking. When a planet orbits extremely close to its star, the gravitational interaction becomes so strong that it can slow the planet's rotation until it matches its orbital period. The result is synchronous rotation. One hemisphere permanently faces the star in eternal daylight, and the opposite hemisphere is turned away in eternal night. This is not a maybe for planets in the tight habitable zone of a red dwarf. It is a near certainty. For a world like L98-59e, this creates a planetary configuration with no Earth-like analogue. The day side would be in constant, unending solar glare, while the night side would be a frozen, starless expanse. The transition region, the terminator line, would be a narrow band of perpetual twilight. This setup poses the first great challenge for climate and habitability. Without rotation to evenly distribute stellar energy, you risk a planet with an extremely hot pole and an extremely cold pole. For liquid water to exist globally, the planet's atmosphere must be exceptionally efficient at transporting heat from the day side to the night side. A thick atmosphere with strong winds could, in theory, circulate enough warmth to prevent the night side from freezing solid and moderate the scorching day side. But if the atmosphere is too thin, the contrast would be absolute, potentially creating a world with a lava hemisphere and an ice hemisphere, with only a sliver of in between. The second, and perhaps more threatening consequence of this closeness is the stellar environment itself. Red dwarfs, especially in their first several billion years, are notoriously tempestuous. They're prone to frequent and powerful flares, sudden violent eruptions that can boost the star's output of X-rays and ultraviolet radiation by orders of magnitude in minutes. A planet like L98-59e, sitting only a few million miles from the star, would bear the full brunt of these events. For a nascent atmosphere, this is an existential threat. Persistent high-energy radiation can split apart molecules in the upper atmosphere, allowing lightweight atoms like hydrogen to escape into space, a process known as hydrodynamic escape. A strong flare can blast away atmosphere directly. This means that for L98-59e to have any atmosphere today, it must have either formed with a massive initial envelope that took eons to erode, or it must have robust geological activity that continuously replenishes volatiles through volcanism, or, crucially, it must have a strong global magnetic field. A magnetic field acts as a planetary shield, deflecting the charged particles of the stellar wind and protecting the atmosphere from being stripped away. Whether such a small, likely tidally locked planet can generate and sustain a strong magnetic dynamo in its core is an open question. The tidal forces themselves might help by keeping the interior hot and churning, but it's not a guarantee. This leads to the third point. The very definition of habitability expands beyond just temperature. In the context of a red dwarf system, habitability becomes a checklist of planetary fortitude. 1. The planet must be in the orbital zone where stellar flux allows for theoretical liquid water. 2. It must have an atmosphere thick enough to provide pressure, redistribute heat, and offer chemical complexity. 3. That atmosphere must be robust enough to have survived billions of years of intense stellar activity. 4. The planet likely needs a magnetic shield to aid in that atmospheric retention. And 5. It needs a source of long-term climate stability, which on an ocean world might be tied to ocean chemistry and geothermal cycles, rather than the silicate weathering we see on continents. Therefore, when we say L98-59e is in the habitable zone, we are really saying it has passed the first most basic orbital test. The next 4 tests are what future observations, particularly with the James Webb Space Telescope, will begin to investigate. The star's history is also a critical part of this equation. L98-59 is estimated to be several billion years old. If it went through a prolonged period of extreme hyperactivity in its youth, the planets we see today may be the survivors of that bombardment, their atmospheres sculpted by that early violence. A planet like E may have started as a mini-Neptune with a huge hydrogen envelope that was completely stripped, leaving behind a water-rich core. Or it may have always been a volatile, rich world that weathered the storm. Understanding the star's current flare rate and its past behaviour, possibly inferred from studies of similar age red dwarfs, is essential to piecing together the planetary biographies. The compact nature of the system also means the inner planets, including E, likely formed closer in from a denser part of the protoplanetary disk. This challenges old notions that the inner regions around red dwarfs would be too hot for water ice, suggesting instead that water-bearing materials could have been incorporated directly into these worlds from the start, which aligns with the ocean world hypothesis for planet E. So, the habitable zone around L98-59 is not a serene, sun-dappled region like we might imagine. It is a cosmic frontier, a region of intense stellar gravity, punishing radiation, and radical planetary climate dynamics. It is a zone where survival is the first prerequisite for habitability. This makes the discovery of a planet like E not less exciting, but more so. It represents a candidate that has, at the very least, survived in this demanding environment for billions of years. If it also possesses a thick atmosphere and a global ocean, it tells us that nature can indeed meet this formidable checklist, that planets can build stable, complex environments under these red suns. And because red dwarfs make up about 75% of all stars in the Milky Way, this means the galaxy's most common real estate could be peppered with such hardy, tidally locked worlds. Our own solar system, with its widely spaced, rapidly rotating planets in the quiet habitable zone of a yellow dwarf, might be the atypical one. The L98-59 system, therefore, is giving us a masterclass in the most common pathway for planetary systems in the cosmos. Its habitable zone is a test chamber for the physical processes that govern most terrestrial planets. By studying it, we are not just exploring one star, we are calibrating our understanding for thousands of other systems already discovered and millions more to come. The promise of a 98-59e is the promise that within the harsh constraints of a red dwarf's realm, nature might still find a way to create a stable, wet and potentially chemical-rich environment. It pushes us to think beyond Earth-centric models of day and night, of seasons, of magnetosphere generation. It forces our instruments to their limits to answer whether such a world can truly be a home, or if it remains a beautiful, intricate prison, forever divided between fire and ice. The search for an answer is what makes this small, faint star and its family of fast-orbiting worlds one of the most important stories in modern astronomy. All this talk of habitable zones, ocean worlds, and atmospheric survival leads inevitably to the next pressing question. How do we go from speculation and modelling to actually knowing what's there? How do we lift the veil on these distant points of light and sniff the air of another world? This is where the story of L98-59 collides with one of the most ambitious scientific instruments ever built, the James Webb Space Telescope. Webb isn't just another telescope. It's a machine designed to answer the very questions this system poses. Its mission, in part, is to transform planets like L98-59e from intriguing dots on a graph into characterized worlds with known atmospheric properties. So, let's talk about how that actually works, and why this system is such a perfect laboratory for Webb's extraordinary capabilities. The dream is atmospheric characterization, and the primary tool for a transiting system like this is a technique called transmission spectroscopy. Here's the basic idea. When a planet transits its star, it doesn't just block the star's light like a simple disk. If the planet has an atmosphere, a tiny additional fraction of starlight, think thousandths of a percent, skims through the atmospheric limb, the thin ring of gas around the planet's edge, before reaching our telescopes. As this light passes through, molecules in the atmosphere absorb specific wavelengths, leaving behind minuscule fingerprints in the star's spectrum. It's as if the atmosphere imprints a barely perceptible barcode on the starlight. Decoding that barcode reveals the atmosphere's chemical composition. Doing this from 35 light-years away is, to put it mildly, incredibly hard. The signal is astoundingly faint, buried in noise and easily mimicked by stellar activity like spots and faculae. This is where the James Webb Space Telescope's design is revolutionary. First, it operates primarily in the infrared. Cool red dwarf stars like L98-59 emit most of their light in the infrared, meaning there's simply more star signal for Webb to collect. Second, its massive 6.5-metre primary mirror gathers an enormous amount of light, allowing it to measure these tiny spectral dips with unprecedented precision. Third, its suite of instruments like NIR-SPEC and MIRI can spread light out into very detailed spectra, precisely where molecules like water, carbon dioxide and methane have their strongest absorption features. Now, why is L98-59 such a particularly good target for this? It comes down to geometry and contrast. The planets in this system are relatively large compared to their star. Because L98-59 is a small red dwarf, the size ratio between the planets and the star is more favourable. A planet transiting a small star blocks a larger percentage of its light, and its atmosphere, proportionally, obscures a larger fraction too. This makes the atmospheric signal slightly stronger, a bit easier to pick out from the noise. Astronomers call this the inflation factor. It's like trying to study the atmosphere of a pea passing in front of a grapefruit versus a pea passing in front of a ping pong ball. The signal from the ping pong ball setup is more pronounced. So, what will Webb actually be looking for when it turns its gaze to this system? The first and most fundamental molecule is water vapour. Detecting water vapour in the atmosphere of L98-59e would be a monumental confirmation. It would verify that the key ingredient for life as we know it is present in the habitable zone of a nearby star, and it would lend powerful support to the ocean world hypothesis. A strong water signal could indicate a thick, steamy atmosphere or even the presence of clouds, but Webb can look for more than just water. Carbon dioxide is another major target. It's a common stable gas in planetary atmospheres and a powerful greenhouse regulator. Finding it would tell us about the planet's atmospheric pressure and its capacity to trap heat, which is crucial for understanding its climate, especially on a tidally locked world. Methane is a particularly intriguing though tricky signature. On Earth, most methane is produced biologically. On other worlds, it can also be produced by geological processes like serpentinization. A detection of methane alongside carbon dioxide, especially if water is also present, would point to a chemically active world with potential subsurface or even biological processes. However, scientists must be extremely cautious. The star's own activity can create spectral features that masquerade as planetary signals. Distinguishing a true planetary atmosphere from the complicated fingerprint of a flickering red dwarf is the single biggest challenge in this work. It will require not just observing the planet during transit, but also meticulously monitoring the star's behaviour before, during and after the transit to subtract its influence. This means many, many hours of Webb's precious time dedicated to this one system. The observations will also look for the absence of features. A flat, featureless spectrum during transit would be a powerful, if disappointing, result. It could mean the planet has no atmosphere at all, or that it's shrouded by very high reflective clouds that obscure our view of the lower atmosphere. For the inner planets, B and C, a flat spectrum would support the theory that these worlds have been stripped bare. For Planet E, it would be a more surprising and perhaps sobering outcome, suggesting that even in the habitable zone, atmospheres might not survive. But let's say Webb does detect an atmosphere on L98-59E. The work is far from over. The next step is to try to understand the structure of that atmosphere. Is it thick or thin? Is it clear or hazy? Does it have clouds? And if so, at what altitude? This involves more detailed modelling of the transmission spectrum, looking at the shape and depth of the absorption features. A thick, extended atmosphere will produce deeper absorption lines. Clouds will mute the features of molecules below them. Haze particles can scatter light in distinctive ways. Furthermore, astronomers might attempt secondary eclipse observations. This is when the planet disappears behind the star. By measuring the infinitesimal drop in the total infrared light as the planet's own thermal emission is blocked, Webb can estimate the planet's dayside temperature. For a tidally locked world, this is the temperature of the permanent dayside hemisphere. Comparing this measured temperature to a simple model prediction tells us about the atmosphere's heat redistribution efficiency. A much hotter dayside than expected suggests a thin or absent atmosphere. A more uniform temperature points to a thick atmosphere efficiently moving heat around. Over time, with enough transits and eclipses, a crude but revolutionary picture of this distant world can be assembled. We could move from knowing Planet E is in the habitable zone to stating Planet E has a thick atmosphere containing water vapour and carbon dioxide, with a dayside temperature suggesting moderate heat circulation. That is a quantum leap in knowledge. It transforms the planet from a speculative possibility into a data-driven reality. This process is not fast. It will take multiple transits. Each transit of Planet E occurs at every 12.8 days to gather enough photons for a clear signal. It requires a coordinated effort between Webb, ground-based telescopes monitoring stellar activity, and teams of analysts working for months to vet the data. But the potential payoff is why we built the telescope in the first place. L98-59 serves as a perfect test case, a nearby system where all the conditions align to push our characterization techniques to their limit. Success here paves the way for studying other, fainter, more distant systems. It validates the methods. In a very real sense, Webb is looking at L98-59 not just to understand that one system, but to learn how to read the atmospheres of countless others waiting to be studied. It is the opening of a new sense, allowing us to not just see other worlds, but to begin to taste their air, to sense their climate, and to take the first tentative step in assessing whether they could be anything like home. The dream is no longer just to find planets, it is to know them. And with Webb trained on this faint red star 35 light-years away, we are on the precipice of doing exactly that, turning points of light into places and speculation into science. The meticulous atmospheric scrutiny planned for the James Webb Space Telescope only works because of a fundamental and, to our earthbound perspective, bizarre characteristic of this system: the sheer speed at which everything happens. We've mentioned the orbital periods in passing: 2.25 days, 3.7 days, 12.8 days, but it's worth pausing to truly absorb what that means for the physics and the lived experience of these worlds. The phenomenon of ultra-rapid orbits around a star like L98-59 isn't just a curious footnote, it is the central, defining rhythm of the entire system, shaping everything from climate to geology to our very ability to study it. To understand why these years are so absurdly short, we need to revisit a cornerstone of orbital mechanics, Kepler's third law. This law establishes a precise mathematical relationship between a planet's distance from its star and the time it takes to orbit. The formula tells us that the square of the orbital period is proportional to the cube of the semi-major axis, which is essentially the average orbital distance. In simpler terms, planets that are closer to their star orbit much, much faster. For a star with the same mass as our Sun, a planet at Mercury's distance orbits in about 88 days. But L98-59 is not like our Sun. It has only about a quarter of the Sun's mass. Lower stellar mass makes the gravitational grip weaker, which, for a given distance, actually allows a planet to orbit slower. However, the crucial factor here is the asterisk distance asterisk. To receive enough warmth to even be in the discussion for habitability, a planet around this faint star must orbit asterisk drastically asterisk closer in than Mercury does to the Sun. This combination, extremely close orbits asterisk and asterisk a lower stellar mass, creates these astonishingly short years. The math works out that at these tiny distances, the effect of proximity overwhelmingly wins, slinging the planets around at breakneck speeds. Imagine the innermost world, Planet B, completing a full celestial circuit in roughly the time it takes for a long weekend to pass on Earth. From its perspective, if it had a perspective, the star would be a gigantic fixed fixture in the sky due to tidal locking, but the background of stars would whip around in a blur every 2.25 days. This rapid orbital motion has profound and inevitable consequences. The most significant is the tidal locking we've discussed, but it's worth understanding the mechanics. The same gravitational forces that cause ocean tides on Earth, when applied over very short distances and over billions of years, act as a brake on a planet's rotation. The closer the planet, the stronger this tidal braking force. For planets in the habitable zone of a red dwarf, the process is so efficient that it likely locks them within a relatively short time, geologically speaking. This means their rotation periods become exactly equal to their orbital periods. So Planet E's day is 12.8 Earth days long, and its year is also 12.8 Earth days long. One side forever faces the star, the other forever faces the cold void. This single fact dictates all future climate models for that world. But these ultra-fast orbits also create a unique and potentially beneficial scenario for atmospheric circulation. On Earth, our 24-hour rotation cycle drives major weather patterns. On a tidally locked world, the driving force is the extreme temperature difference between the permanent day and night hemispheres. This can, in theory, generate ferocious planet-spanning winds, rushing from the hot, high-pressure day side to the cold, low-pressure night side. If the atmosphere is thick enough, these winds could distribute heat with remarkable efficiency, potentially preventing the night side from freezing into a solid ice sheet and moderating the day side's scorching heat. The planet's rapid orbit around the star adds another layer, the Coriolis effect, which on Earth deflects winds and helps create cyclones and anticyclones. On a slowly rotating, tidally locked world, this effect is minimal, so the atmospheric flow might be simpler, a direct, massive convection cell from this substellar point outward. For astronomers, these dizzyingly fast orbits are not a challenge but a gift. They make the system a prolific data factory. Because the planets transit so frequently, opportunities to observe those transit events, the key to measuring atmospheres, come around again and again with startling regularity. If you miss a transit of Planet E, you only have to wait 12.8 days for the next one. For the inner planets, the wait is even shorter. This allows for the rapid accumulation of signal. To build up a high-quality transmission spectrum with the James Webb Space Telescope, you need to stack the data from many transits to beat down the noise. A system with orbits measured in days means you can collect dozens of transits in a single Earth year. For a similar planet in an Earth-like 365-day orbit around a Sun-like star, you'd get one chance per year, making the same measurement take decades. L98-59 offers a compressed timeline for discovery. The same principle applies to the radial velocity method. The planet's rapid orbit means its gravitational tug creates a quickly repeating predictable wobble in the star, which is easier to detect and confirm against background noise than a slow, year-long stellar sway. This rapid cycling also opens the door to studying weather and temporal changes. If clouds form and dissipate on Planet E, or if massive storms erupt, observations over successive orbits might, in the far future with immense telescopes, be able to detect changes in the planet's brightness or spectral features. We could in essence watch the weather patterns on an exoplanet evolve over weeks and months, not centuries. From a planetary formation standpoint, these tight orbits are a clue. They suggest that the protoplanetary disk around the young L98-59 was rich in material very close to the star. The planets likely formed asterisk in situ asterisk, or migrated inward very early, and then their orbits stabilised into this compact resonant or near-resonant configuration. The fact that they all fit within a distance smaller than Mercury's orbit around our Sun illustrates how much planetary real estate is packed into these red dwarf systems. There is no room for gas giants here. This is the domain of terrestrial worlds, shoulder to shoulder. For a hypothetical observer on the day side of Planet E, the cosmic clock would be utterly alien. There would be no sunrise or sunset. The sun would hang unmoving in the sky, perhaps librating slightly due to orbital eccentricities. The only marker of a year would be the slow parade of constellations, completing a full circle in the night sky of the opposite hemisphere, a circle completed every 12.8 days. Seasons, as we know them, wouldn't exist, as the planet's axis likely isn't tilted in a meaningful way. Instead, seasons might be driven by changes in the star's activity, periods of intense flaring versus relative calm. The passage of time would be measured in orbits, not rotations. This compression of time and space forces us to expand our imagination. Life, if it existed on such a world, would evolve under a fixed sun and an eternally starry night. Photosynthetic organisms would be anchored on the dayside, but would need protection from the constant unfiltered glare. The concept of circadian rhythms would be tied to other cycles, perhaps geothermal or tidal, rather than a daily light-dark cycle. The entire framework of time that governs biology on Earth is absent. In the end, the ultrafast orbits of the L98-59 system are more than a curiosity. They are the direct, inescapable consequence of the most common type of star in the galaxy being small and faint. They represent the default orbital speed for planets and habitable zones across the Milky Way. Our leisurely 365-day journey around our bright yellow sun is the galactic outlier. By studying the dynamics, climate and atmospheres of worlds like these, we are learning about the most typical planetary environments in the cosmos. Their speed is a gift to our science, providing rapid data and clear signals. Their implications are a challenge to our Earth-centric biases, showing us just how strange and varied the conditions for potential life might be. The rhythm of L98-59, a rhythmic ticking measured in single Earth days, is perhaps the true heartbeat of the galaxy, a fast, quiet pulse from a small red star, reminding us that our own celestial cadence is the exception, not the rule. The mind-bending reality of those ultra-fast orbits and permanent daysides leads us directly into the most captivating possibility raised by the data on Planet E, that it might not just be a wet world, but an true ocean world, a globe shrouded in a deep abyssal sea. This hypothesis transforms the conversation from one about surface conditions to something far more profound and alien, the concept of deep habitability, where life, if it exists, would be utterly divorced from the sky above and the sun that hangs in it. The idea that L98-59e could be composed of up to 30% water by mass is not a detail, it is a paradigm shift. It suggests a planetary structure radically different from Earth's. Earth is a rocky planet with surface oceans that are, in terms of planetary scale, a mere shimmering film. Our water makes up less than 1% of Earth's mass. If Planet E has 30 times that proportion, the entire model flips. The likely scenario is a layered world, a metallic core, a rocky mantle, and then an immense layer of water hundreds of kilometers thick, topped by an atmosphere. Under the immense pressures at the bottom of such an ocean, water could form exotic high-pressure ices, creating a barrier between the liquid sea and the rocky seafloor, a water mantle with a frozen floor. Or, if the planet is warm enough internally, the ocean could remain liquid all the way down to a rocky seabed, interacting directly with the planet's geology. This distinction is crucial for habitability. A direct rock-water interface is what astrobiologists get most excited about. On Earth, life thrives not just in sunlit surface waters, but in the deepest, darkest trenches, fueled by chemical energy from hydrothermal vents. These are cracks in the seafloor where geothermally heated water, rich in minerals from the planet's interior, gushes out into the cold ocean. The chemical disequilibrium between this hot, mineral-laden fluid and the surrounding seawater provides a potent energy source for chemosynthetic microbes. which form the base of a complex and independent ecosystem that never sees the sun. If L98-59 has a liquid water ocean in contact with a geologically active rocky core, it could host precisely these kinds of environments. The entire planet could be a single, global bioreactor, with life potentially thriving around volcanic arcs or hydrothermal vent fields on its seafloor, completely isolated from the tumultuous irradiated stellar environment above. This is the essence of deep habitability, a biosphere sealed beneath a roof of ice or a thick atmosphere and ocean, protected from stellar flares, ultraviolet radiation, and even asteroid impacts. It is a form of life that is inherently more resilient to cosmic catastrophes. The challenges, however, are formidable. The first is energy. Hydrothermal vents on Earth are driven by plate tectonics and mantle convection, processes fueled by Earth's internal heat from radioactive decay and residual accretion energy. For a smaller planet like L98-59e, this internal heat source might be less potent. However, tidal forces come to the rescue. The planet's eccentric orbit and gravitational interactions with its siblings could flex its interior through tidal heating, providing a supplementary and potentially long-lived geothermal energy source, much like the process that keeps the subsurface ocean of Jupiter's moon Europa liquid. This tidal kneading could power volcanic activity on the seafloor for billions of years, sustaining hydrothermal systems. The second challenge is nutrient cycling. On Earth, the surface biosphere and the deep sea are connected. Nutrients from weathered continents wash into the oceans, and organic matter from the surface drifts down to the depths in a marine snow. In a completely enclosed global ocean with no land masses, this cycle is broken. All essential elements for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, must come from the planet's initial endowment and be recycled through purely oceanic and geological processes. The hydrothermal vents themselves would be both creators and recyclers, leaching minerals from the rock and providing a continuous flow of chemicals. But whether such a system could achieve the complex large-scale recycling needed to sustain a diverse, planet-wide biosphere over geologic epochs is unknown. It might be a world where life is possible, but only in isolated, sparse oases around vent systems, never evolving into the complex interconnected web we see on Earth's surface and in its oceans. The third and perhaps most daunting challenge is for us: detection. How do we find signs of life, a biosignature in a global ocean buried under a thick atmosphere and possibly an ice lid? Traditional atmospheric biosignatures like oxygen or methane produced by surface photosynthesis are off the table. Any atmospheric gases would be the product of geologic outgassing or the byproducts of a deep-sea biosphere that slowly diffuse upwards. Methane could be a clue, but as mentioned, it has geological sources too. A more tantalizing, though incredibly difficult to detect, signature might be a chemical disequilibrium in the atmosphere that is hard to explain without biology. For instance, the simultaneous presence of methane and oxygen in an atmosphere with liquid water is a strong potential biosignature on Earth, but on an ocean world, oxygen might never build up in the atmosphere. Scientists might instead look for more subtle hints, an overabundance of certain complex organic molecules, or a specific isotopic ratio in atmospheric gases that favours biological processes. However, teasing these signals from the noise of abiotic chemistry and stellar interference will push the limits of even the James Webb Space Telescope and its successors. We may need to infer the presence of life indirectly, by first confirming the ocean, then the geological activity, and then building a statistical case that the observed atmospheric chemistry is most consistent with a biosphere. The possibility of a deep habitable environment also forces us to reconsider the star's threat. The punishing flares from L98-59 that could sterilise a surface world are irrelevant to life in a kilometres deep ocean. The water column itself is a superb radiation shield. The real threat to a subsurface biosphere would be the loss of its heat source. If tidal heating ceased and geological activity died down, the vents would go cold and the life they support would perish. But given the star's trillion-year lifespan, the planetary system has almost unimaginable time for such processes to ebb and flow. The ocean world hypothesis for L98-59e, therefore, opens a window into a completely different astrobiological pathway. It suggests that the most common life in the galaxy might not be on surface continents under an open sky, but in eternal darkness, under crushing pressure, clustered around cracks in the seafloor of alien oceans. It means that a planet need not be Earth-like in appearance to be teeming with life. A world that from the outside appears as a featureless, steamy blue marble or an icy globe could harbour a universe of complexity within. This shifts the focus of the search for life. While we will still eagerly study the atmospheres of any terrestrial planet in the habitable zone, the discovery of a confirmed ocean world like L98-59 would immediately prioritise the search for indirect signs of subsurface geological activity and the subtle chemical traces of a hidden biosphere. It teaches us that habitability has layers, both literal and figurative. The surface may be uninhabitable, while the depths are not. For L98-59e, its surface, if it even has a traditional surface, might be a uniform, hot ocean or a global ice cap, but its soul, its potential for life, would be in the dark, hot, mineral-rich waters meeting the rock of its core. It is a reminder that life is tenacious and opportunistic, seeking out energy wherever it can be found, whether from a nearby star or from the slow heat of a planet's heart. As we continue to study this remarkable system, the question of whether it is an ocean world remains paramount, because the answer doesn't just describe one planet, it defines a whole category of potential homes for life in the cosmos, hidden beneath the waves of red dwarf stars. The idea of a deep, shielded biosphere thriving around hydrothermal vents is a compelling counterpoint to the most glaring threat posed by the star L98-59 itself. While life might hunker down in the abyssal dark, safe from the chaos above, the planetary surface and any atmosphere face a far more hostile reality. This brings us to the central antagonist in the story of red dwarf habitability, stellar activity. L98-59, while possibly quiet now, is a relatively young star, estimated to be several billion years old. In the life of a red dwarf, that still counts as youthful enough to possess a significant temper. This inherent volatility is not a minor detail. It is the defining environmental factor that has likely sculpted the entire system we see today. Red dwarfs are convective throughout their interior, unlike sun-like stars. This efficient churning, combined with their rapid rotation when young, amplifies their magnetic dynamo, leading to intense magnetic fields. These fields buckle and twist, storing enormous energy that is released suddenly in the form of stellar flares and coronal mass ejections. A flare is a catastrophic explosion on the star's surface that, in moments, can increase its output of X-ray and ultraviolet radiation by 100 or even 1,000 times. Following a flare, a coronal mass ejection can blast 1 billion tons of charged particles into space at a significant fraction of light speed. For planets like those in the L98-59 system, orbiting so close, these events are not distant spectacles. They are direct atmospheric assaults. The impact of such a barrage on a developing or established atmosphere can be devastating. The high-energy ultraviolet and X-ray photons are particularly damaging. They have enough energy to break apart molecules in the upper atmosphere, a process called photodissociation. Water vapour, for example, can be split into hydrogen and oxygen. The lightweight hydrogen, once liberated, can achieve escape velocity and bleed off into space, irreversibly lost. This is how a planet can lose its water over geologic time. The charged particles from coronal mass ejections batter the planetary magnetic field, if one exists, and can strip away atmospheric ions in a process known as sputtering. For a planet without a strong magnetic shield, the stellar wind itself, a constant stream of particles, can erode the atmosphere slowly but surely, like a cosmic sandblaster. This presents us with the critical historical question for L98-59's planets. What was the star like in its first billion years? Many red dwarfs are thought to go through a protracted phase of extreme hyperactivity after their formation, a violent infancy that could last for 1 billion years or more. During this time, flare rates could be hundreds of times higher than today, and the stellar wind would have been ferocious. The planets we see now, including the promising ocean world E, would have been bathed in this relentless fury during their most formative epoch. Their current states are the end result of that trial by fire. This forces us to consider two starkly different narratives for a planet like L98-59e. Narrative 1. It formed as a volatile, rich world, a mini Neptune with a thick primordial hydrogen and helium envelope. The star's relentless early activity then stripped away this entire gaseous shroud over hundreds of millions of years, leaving behind the stripped core, a dense, rocky and water-rich world. This is a plausible formation path for some super-Earths. Narrative 2, it formed more like a larger version of Earth, with a secondary atmosphere outgassed from its interior. To survive, this atmosphere would have had to be massive enough, or protected by a strong enough magnetic field to weather the stellar onslaught. It might have lost vast quantities of water early on, but retained enough to maintain a deep ocean and a dense, steamy atmosphere. The planet we see today is the survivor, the one that held on. The difference between these narratives is the difference between a world born with a thick blanket that was torn away and a world that fought to keep its coat in a hurricane. The evidence for this violent past may be written in the present-day atmospheres, or lack thereof. If Planet B and C are airless, it is strong evidence that the star's erosive power at close range was overwhelming. If Planet E has a substantial atmosphere, it tells us that either it started with an immense reservoir, or it developed a robust protective mechanism early on. This is why understanding the current activity level of L98-59 is so crucial. By observing it with X-ray telescopes like Chandra or XMM Newton, astronomers can measure its present-day flare frequency and strength. While it is likely quieter now, it still might experience significant flares. Observing one such event while the James Webb Space Telescope is studying a planetary transit could be scientifically golden, showing us in real time how the planet's atmosphere responds to a sudden blast of radiation. It would be a direct experiment in atmospheric erosion. The necessity of a planetary magnetic field becomes a central character in this drama. For Earth, our global magnetic field acts as a shield, deflecting the solar wind and protecting our atmosphere. For a tidally locked planet like L98-59e, generating a magnetic field is more complicated. The dynamo effect requires a convecting, electrically conducting fluid in the planet's interior, usually a molten iron core. Tidal locking could potentially help by providing tidal heating that keeps the interior hot and churning, but it might also lead to a more stratified interior. Some models suggest a tidally locked planet might even develop a strange asymmetric magnetic field, stronger on the day side than the night side. Whether Planet E has any magnetic shield at all is an open question, and one we cannot directly answer yet. Its presence or absence would be a major factor in its atmospheric history. The concept of habitability around a star like this, therefore, is not a static state achieved by orbital position alone. It is a dynamic condition, a balance between the destructive power of the star and the defensive resilience of the planet. It is a war of attrition fought over billions of years. A planet might reside in the perfect orbital zone for liquid water, but if its atmosphere was shredded in its youth, it is now a barren rock. This reframes our search. We are not just looking for planets in the habitable zone, we are looking for asterisk survivors asterisk. L98-59e, if it is a water world with an atmosphere, is a prime candidate for a survivor world. Its potential habitability is not just about current temperatures, but about its demonstrated toughness over cosmic time. This also affects the potential surface conditions. Even if the planet retained a thick atmosphere, frequent flares would bathe the surface in biologically harmful UV radiation, posing a challenge for any surface life that might evolve. This provides another argument for the deep ocean hypothesis. The ocean itself is the best radiation shield. The flares that would scorch a surface biosphere are reduced to a faint, harmless shimmer in the deep, dark waters where chemosynthetic life could dwell. In studying LR98-59, we are therefore conducting a forensic investigation into stellar-planetary relations. The planets are artifacts shaped by the star's historical behaviour. By measuring their densities, searching for their atmospheres, and characterising the star's current mood, we are piecing together a biography of violence and resilience. This knowledge is not just for this one system. It applies to the legions of red dwarf systems we've already found, and the countless more we will discover. If we can determine that planets in the habitable zones of quiet, older red dwarfs can retain atmospheres, it vastly increases the number of potentially life-bearing worlds in the galaxy. If we find that even these worlds are systematically stripped, it would suggest that the quieter, longer-lived yellow dwarfs like our Sun, though less common, might be the more reliably hospitable hosts. L98-59, with its mix of a potentially temperate ocean world and a history of stellar storms, sits at the crossroads of this critical investigation. It shows us both the promise and the peril of the most common stellar real estate in the universe, teaching us that a star's temperament is just as important as its temperature when judging the potential for life next door. The constant tension between a star's violent history and a planet's struggle to survive highlights why getting detailed data is so critical. And here the L98-59 system holds a final, overwhelming advantage that makes all this scrutiny possible: its location. At a distance of roughly 35 light-years, this system is, in astronomical terms, right in our backyard. This proximity isn't just a fun fact, it is the single most important practical factor that elevates this system from being merely interesting to being utterly transformative for the field of exoplanet science. That 35 light-year gap is a bridge that allows our instruments to perform near miracles, turning faint whispers of signals into shouts we can actually analyse. Think of it this way: the further away a light source is, the dimmer it appears, and the more its signal spreads out and gets lost in the cosmic noise. For the delicate work of measuring planetary transits, stellar wobbles, and especially atmospheric spectra, distance is the enemy. L98-59, by being so cosmically close, gives us a brighter, clearer, and more stable signal across every wavelength we can observe. This begins with the very discovery method. The transit signal, that tiny dip in starlight, is stronger because the star itself appears brighter to our telescopes. This makes the initial detection more robust and allows even smaller planets, potentially the size of Earth or Mars, to be found with greater confidence in the data. For the radial velocity method, a brighter star means we can collect more photons in a given observation time, allowing spectrographs like espresso to measure the star's wobble with incredible precision, down to centimetres per second. This precision is what confirmed the planet's masses and densities, moving them from anonymous blips to characterised worlds. Without this proximity, the same planets around a more distant star might have remained hidden, or their masses would be unknown, leaving us with far more guesswork. But the real magic of this short distance is what it enables for the future, particularly for atmospheric studies with the James Webb Space Telescope. The transmission spectroscopy technique relies on detecting the incredibly faint absorption fingerprints of molecules in a planet's atmosphere as starlight filters through it. The amount of light we receive from the star sets a hard limit on how good that data can be. A brighter star means more photons to work with, which means we can achieve a higher signal-to-noise ratio in less time. For a demanding and time-constrained observatory like Webb, every hour of observation is precious. Studying L98-59e is simply more efficient than studying a similar planet around a fainter, more distant star. We can get a clear result with fewer transits, or we can use the same number of transits to achieve an even more detailed spectrum. This proximity also makes the system a prime target for the next generation of giant ground-based telescopes, like the extremely large telescope currently under construction in Chile. With a primary mirror 39 meters across, the ELT will have unprecedented light-gathering power and resolution. One of its goals is direct imaging and spectroscopy of exoplanets. While directly imaging a planet as close to its star as those in L98-59 is extremely difficult, the system's outer regions might yet hold undiscovered colder planets on wider orbits. The ELT, aided by advanced coronagraphs, might be able to directly detect and take a spectrum of such a world, effectively taking a picture of it and analysing its atmosphere without needing a transit. This would be a completely independent method of characterisation, complementing the transit studies of the inner worlds. Furthermore, the system's location in the sky is favourable for long-duration monitoring from both hemispheres, allowing for almost continuous observation campaigns that can track stellar activity and refine orbital parameters. This combination of factors transforms L98-59 into a natural laboratory, a testbed where we can develop, refine and benchmark the techniques that will define the next era of astronomy. It is a system where we can practice. Before we point our most powerful tools at Earth-sized planets around farther, fainter stars, we need to ensure our methods and models work. L98-59 with its multiple well-spaced transiting planets of varying sizes and orbits around a bright nearby star, provides the perfect controlled environment for this calibration. We can test our atmospheric retrieval algorithms here, where we have multiple planets to compare. We can learn how to distinguish between stellar activity signals and genuine planetary atmospheric features in a system where we can monitor the star with exceptional clarity. Any lesson learned here about data processing, noise reduction, or model interpretation can be directly applied to thousands of other systems, magnifying the impact of this single study. The proximity also opens the door to more exotic and ambitious measurements in the coming decades. As technology advances, astronomers hope to use a technique called interferometry to combine the light from multiple telescopes spread across the globe, or even in space, to create a virtual telescope with a resolution equivalent to one the size of the distance between them. Such an instrument could, in theory, resolve the disk of a large exoplanet or map temperature variations across its surface. A bright nearby target like L98-59 would be a logical first candidate for such an attempt. We might one day have a crude map showing the hotspot under the permanent star and the colder night side, confirming the tidal locking model directly. Additionally, the system will be a key target for future space missions specifically designed for atmospheric characterization, like the European Space Agency's Ariel mission, or NASA's concept for a habitable worlds observatory. These missions will have L98-59 high on their target lists precisely because it offers the clearest possible signal for a small, rocky world in the habitable zone. In a very real sense, this system is a gateway. It is our nearest best opportunity to answer the question: can small rocky planets around the most common stars retain atmospheres and conditions suitable for liquid water? The answer we get here will shape the statistical predictions we make about the entire galaxy. If L98-59 shows a thriving, water-rich atmosphere, it suggests such outcomes are possible even after a violent stellar youth. If it appears as a barren rock or a steamy, uninhabitable hellscape, it would suggest the challenges are too great, narrowing the search for life to quieter, less common stars. This is why astronomers are so focused on this particular star. It's not just about one system, it's about using the most accessible example to unlock secrets about billions of others. Its proximity provides the signal strength, the observational flexibility, and the long-term potential that makes it a unique asset. The light that reaches us today left that star when many of us were children, a mere cosmic blink ago. In the vast scale of the galaxy, 35 light-years is a stone's throw, and it is that fortunate accident of location that allows us to peer so deeply into this compact family of worlds. We are not just observing a distant point of light, we are conducting a detailed examination of a neighbour, and in doing so, we are building the textbook that will teach us how to understand the rest of the distant, faint points that fill the night sky. A98-59 is the benchmark, the standard against which we will measure other systems, and its closeness is the gift that makes that possible, turning it from a subject of study into a foundational tool for all of exoplanet science. Having established why this nearby system is such a perfect laboratory for our tools, it becomes almost irresistible to place it side by side with the only planetary system we know intimately, our own. The comparison between the compact family of L98-59 and our spacious solar system is not just an academic exercise. It's a stark lesson in cosmic diversity that forces us to question which architectural style might be the more common blueprint across the galaxy. The differences are profound and begin with the most obvious feature: scale and spacing. In our solar system, the 4 terrestrial worlds, Mercury, Venus, Earth, and Mars, are spread out over a vast gulf of space. Mercury orbits at an average distance of about 58 million kilometres from the Sun. Mars is out at around 228 million kilometres. The rocky planets have room to breathe, each occupying its own distinct orbital lane with the asteroid belt as a broad divider before the realm of the gas giants. Now, consider L98-59. All 4 of its known planets could fit comfortably within the orbit of Mercury around our Sun, with room to spare. Their orbits are measured in single-digit million kilometres, and their years in days, not months or years. This is a system of extreme density, a miniature solar system where the planets are close neighbours, not distant cousins. This compactness has immediate physical consequences. In our system, tidal forces from the Sun are relatively weak on the inner planets, allowing them to retain fast rotations, though Mercury is in a slow spin orbit resonance. In L98-59, the proximity guarantees that the planets are tidally locked, a condition that dramatically reshapes their potential climates and geology. Furthermore, the gravitational interactions between the planets themselves are likely much stronger. They tug on each other, potentially stabilising their orbits through resonances or, in the past, causing migration that shaped the system's layout. Our terrestrial planets, in contrast, have dynamically quieter relationships, their orbits largely settled over billions of years. The next glaring difference is the absence, so far, of any giant planets in the inner system. Our solar system has two gas giants, Jupiter and Saturn, orbiting beyond the frost line, and two ice giants, Uranus and Neptune, further out. Their presence, particularly Jupiter's, is thought to have played a major role in shaping the inner system, perhaps influencing the delivery of water to Earth and helping to clear out debris. In L98-59, there is no sign of a Jupiter-like world lurking close in. This absence may be a key reason why multiple rocky planets could form and persist so near the star. Without a massive gravitational bully in the inner neighbourhood, protoplanetary material could coalesce into several worlds without being ejected or consumed. This supports the idea that compact systems of super-Earths and mini-Neptunes are the default outcome around low-mass stars, while systems with distant gas giants like ours might be a less common variant. The composition of the planets themselves offers another point of contrast. Our inner planets are largely dry, with Earth being the obvious, blessed exception with its surface oceans. Mars shows evidence of past water, but Venus and Mercury are bone dry. The L98-59 planets, based on density, seem to be a mix of rocky and potentially water-rich worlds, with Planet E possibly being a true ocean world. This suggests that the protoplanetary disk around our 9859 was either inherently richer in water ice and volatiles in the inner region, or that the planets formed from water-bearing planetesimals that migrated inward. In our solar system, the prevailing theory is that Earth's water was delivered later by asteroids and comets from the outer system, after the inner region had dried out. The L98-59 system challenges that narrative, showing that water can be baked into the recipe from the very start, even close to the star. The stellar environment is, of course, the most dramatic differentiator. Our Sun is a relatively placid G-type star. It has flares and cycles, but nothing compared to the eruptive fury of a young red dwarf. Earth enjoys a temperate, stable irradiance, with a 24-hour day-night cycle and a yearly seasonal rhythm driven by axial tilt. A planet in the habitable zone of L98-59 is bathed in a different light spectrum, prone to punishing flares, and locked in a permanent embrace with its sun, experiencing seasons defined by stellar activity, not orbital geometry. This means that even if Planet E is technically in the habitable zone, its environmental experience is alien beyond comprehension compared to Earth's. From a search perspective, this comparison explains discovery biases. Our solar system would be far harder to detect from 35 light-years away with current methods. The transits of Earth or Venus across the Sun would be extremely shallow and infrequent, occurring once per year or longer. The radial velocity wobble induced by Earth is minuscule. In contrast, the L98-59 system is practically shouting its presence to our telescopes, frequent deep transits and strong, fast wobbles. This tells us that the exoplanet census we are building is heavily skewed towards systems that are compact and close to their stars, not necessarily because they're more common, though they might be, but because they're infinitely easier to find. We are in essence seeing the low-hanging fruit of the galactic planetary population. This comparison also refines the concept of the habitable zone. In our system, it is a broad, spacious band containing 3 planets: Venus, Earth, Mars, only one of which is truly habitable. In a red dwarf system, the habitable zone is a narrow, tight ring, often containing just one planet. Getting it right in such a constrained space is a different kind of puzzle. The L98-59 system, therefore, acts as a mirror. It shows us that our own cosmic neighbourhood, with its wide orbits, diverse planet types, and a solitary, life-bearing world in the middle of the Goldilocks zone, might be a special, perhaps even rare, configuration. Or it might be one of several viable planetary architectures. By studying this compact system in detail, We learn what variables are flexible and which are essential. Can life emerge without a day-night cycle? Can a magnetic field form on a tidally locked world? Can an atmosphere survive without the protection of a distant Jupiter? These are questions our solar system cannot answer, but L98-59 might. Ultimately, placing these two systems side by side humbles our Earth-centric viewpoint. It demonstrates that the processes of planet formation can produce wildly different outcomes under different stellar hosts. Our familiar clockwork system of separated planets is just one design in nature's catalogue. The crowded, fast-paced miniature system of L98-59 is another, potentially more common design. Understanding both helps us build a universal theory of planet formation, one that can explain the serene spacing of our own home and the intimate embrace of our intriguing neighbour 35 light-years away. This comparison isn't about which is better, it's about understanding the full spectrum of possibilities, teaching us that when we search for life elsewhere, we must be prepared to find it in circumstances far stranger than anything we have ever known at home. The stark architectural differences between our solar system and the compact one around L98-59 naturally lead us to ask how such a system came to be. What specific processes around a small, cool red dwarf star allow for the formation of multiple rocky planets, some potentially water-rich, all crammed into a space smaller than Mercury's orbit? The answer lies in the conditions of the primordial protoplanetary disk that surrounded the infant star, and the story it tells challenges and enriches our understanding of planet formation in the most common stellar environment in the galaxy. When L98-59 was newly formed, it was surrounded by a rotating disk of gas and dust. This is a universal phase of star formation. However, because the star itself is of low mass, the disk was likely also less massive than the one that birthed our solar system. But crucially, it could have been relatively denser in its inner regions. The temperature gradient in the disk is key. Close to the young star, temperatures are high enough to vaporize water ice, creating a snow line or frost line beyond which water can condense into solid ice grains. In a disk around a dim red dwarf, this snow line is located incredibly close to the star, much closer than in our solar system. Some models place it at a distance where Planety orbits today. This means that water ice could have been a readily available building material even in the inner disk. Planetesimals, the early kilometre-sized planetary building blocks, could have formed from a mix of silicate rocks and water ice right there, close to the star. This is a fundamental shift from the traditional view of our own system, where the inner disk was too hot for ice, leading to dry, rocky planets, with water delivered later by icy comets from beyond the frost line. In the L98-59 system, the building blocks themselves might have been wet. This in situ formation of wet planetesimals could directly explain the inferred water-rich nature of Planet E. It didn't necessarily need to migrate inward from the cold outer regions. It could have formed right where it is, from material that already contained a significant fraction of water. The process of accretion from these planetesimals into protoplanets would then proceed. The dense inner disk material, rich in both rock and ice, would allow for the rapid growth of multiple planetary embryos. Because the region is so compact, these growing bodies would interact gravitationally more frequently and strongly than the embryos in our own more spacious inner solar system. They might have scattered each other, collided and merged, eventually settling into the stable, closely packed configuration we see today. The absence of a massive gas giant in the inner system likely facilitated this process. A Jupiter analogue would have gravitationally stirred the region, potentially ejecting material or preventing the calm accretion of several rocky worlds. The fact that we see multiple planets suggests the inner disk was a quiet neighbourhood where planetary accretion could proceed to completion without major disruptive interference from a giant planet. This leads to the question of migration. Did these planets form further out and then migrate inward? This is a common feature in many exoplanet systems, especially those with hot Jupiters. For L98-59, some degree of migration is possible, perhaps even likely, but it would have been a gentle early migration within the gas-rich disk known as Type 1 migration. As the young planets interacted with the surrounding gas disk, gravitational torques could have caused them to slowly drift inward. This migration might have stopped when the gas disk dissipated, leaving the planets parked in their current tight orbits. Alternatively, they could have formed more or less in place, a scenario called in situ formation that is gaining traction for compact systems like this one. The precise orbital spacings and potential resonances between the planets hold clues to this history, which further observations will help decode. The final compositions of the planets are a direct record of these processes. The density of planet B and C suggests they are rocky, with perhaps a small amount of water or other volatiles. Planet E's lower density points to a significant water component. This variety within one system suggests that the accretion process was not uniform. Perhaps Planet E formed from planetesimals that originated slightly further out beyond a local frost line within the disk where ice was even more abundant. Or it could be the result of a giant impact between two protoplanets that mixed rock and water in a specific ratio. The system is a fossil record of the conditions in that disk. Studying it is like doing planetary archaeology, piecing together the distribution of materials and the dynamical events that led to the current configuration. Furthermore, the system's compactness has implications for long-term evolution. The planets are close enough to exert gravitational influences on each other. These interactions can cause subtle changes in orbital eccentricities and inclinations over time, a process called secular evolution. Tidal forces from the star, as we've discussed, are dominant and have led to locked rotations. The internal heat from both accretion and radioactive decay, possibly supplemented by tidal heating from gravitational interactions, could have driven significant geological activity in the past, influencing outgassing and the formation of primordial atmospheres. The early intense flare phase of the star then acted as a filter, potentially stripping away these first atmospheres and leaving behind the evolved worlds we see. In a broader sense, the L98-59 system provides a template. It shows that around the smallest stars, planetary formation is both efficient and capable of producing diverse terrestrial worlds within a tiny orbital space. It suggests that water can be a common ingredient from the start, not a rare late delivery. This has enormous implications for the potential abundance of habitable worlds. If red dwarf systems routinely form multiple rocky planets with significant water content, and if some of those planets can retain their volatiles, despite stellar activity, then the number of candidate worlds for life in the galaxy could be even larger than we've dared hope. By unravelling the formation story of this one nearby system, we are effectively writing the guidebook for understanding the majority of planetary systems in the Milky Way. We are moving from a model based on our own, perhaps a typical solar system, to a model informed by the most common stellar environment. L98-59 is not an oddity. It is likely a standard example of how planets form when the central star is small, faint, and long-lived. Its study is therefore foundational, helping us predict what we will find as we discover thousands more red dwarf systems, and teaching us that the pathways to building worlds are as varied as the stars themselves. Ariel's data will help answer that. On the ground, the era of extremely large telescopes is dawning. The Extremely Large Telescope, the 30-metre telescope, and the Giant Magellan Telescope are all under development. Their primary mirrors, ranging from 25 to 39 metres across, will collect an unprecedented amount of light. For L98-59, these telescopes will pursue several avenues. First, they will dramatically refine the radial velocity measurements. Using advanced spectrographs, they might detect the wobble induced by even smaller, undiscovered planets in the system, perhaps rocky worlds in wider, more temperate orbits that don't transit, or even the gravitational tug of exomoons. Second, they will attempt direct detection. While directly imaging a planet as close to its star as Planet E is a monumental challenge, these telescopes are equipped with sophisticated coronagraphs and adaptive optics systems to blot out the star's glare, might be able to directly capture the faint infrared glow of a colder outer planet in the system, one we haven't found yet. Getting a direct image and a spectrum of such a world without needing a transit would be a revolutionary complement to the transit studies of the inner planets. Beyond imaging and spectroscopy, these giant telescopes will also provide exquisitely detailed monitoring of the host star itself. They will measure its flare activity, star spot cycles, and overall magnetic temperament with a precision that today's telescopes cannot match. This stellar context is vital for interpreting any atmospheric data from the planets. You must understand the painter to fully understand the painting. Further into the future, NASA's concept for a habitable worlds observatory looms large on the horizon. Envisioned as a large ultraviolet optical and infrared telescope designed specifically to image and characterize Earth, like exoplanets, this mission would represent the next quantum leap. If funded and built, it could potentially directly image the reflected light from Planety itself. Instead of just a transmission spectrum gleaned during a transit, you could get a spectrum of the planet's dayside hemisphere, analysing its surface and clouds directly. It might even be able to map broad surface features or weather patterns. For a system as close and well-studied as L98-59, the Habitable Worlds Observatory would be the ultimate tool, potentially turning this planetary family into a set of resolved worlds, not just data points. The technological innovation won't stop at traditional telescopes. Interferometry, which combines the light from multiple telescopes to simulate a single, much larger instrument, holds promise. Space-based interferometry missions, though decades away, could theoretically achieve the resolution needed to actually see a planet like Ye as a distinct dot and measure its temperature variations between the dayside and night side, providing the ultimate confirmation of tidal locking. Closer to the present, continued monitoring with TESS and other transit surveys will search for additional planets via the transit method. The orbits of the known planets might exhibit slight timing variations, a telltale sign of the gravitational pull of another, unseen world in the system. Finding a fifth or even sixth planet, perhaps in a wider orbit, would complete the family portrait and offer new clues about the system's dynamical history and formation. Laboratory work and advanced computer modelling will proceed in tandem with these observations. Scientists will run complex climate simulations for Planet Key under thousands of different assumptions about atmospheric composition, pressure, and ocean depth. They will model the interior structures to understand the possible configurations of its water layer and rocky core. They will simulate the atmospheric erosion processes from stellar flares across billions of years. These models will generate testable predictions that the telescopes can then check, creating a powerful feedback loop between theory and observation. The search for technosignatures, though a long shot, might also eventually include this system. As our own radio and optical transmission technologies become more capable of detecting faint, deliberate signals, a quiet nearby system with a promising habitable zone planet is a logical target for surveys by projects like SETI. While finding any such signal is incredibly unlikely, the comprehensive nature of future study means even this possibility will get a look. In essence, L98-59 has been promoted from a discovery to a benchmark system, a testing ground. Every new instrument, every new technique will be tried out here first. It is the celestial lab rat for exoplanet characterization. The data we gather from it will not only tell the story of these specific worlds, but will also validate the tools and methods we plan to use on thousands of other, fainter systems. It is a foundation stone. The ultimate goal is to move from simply detecting planets to truly understanding them as whole worlds with geology, climate, and potential biology. L98-59, by virtue of its proximity and favourable configuration, is our shortest and clearest path to that goal. The next 2 decades will see this system's file grow from a few pages of basic parameters to a dense volume filled with atmospheric spectra, climate models, magnetic field estimates, and perhaps even the first tantalizing hints of chemistry that we cannot easily explain by geology alone. It represents a continuum of exploration, from the initial detection by TESS, to the atmospheric probing by Webb and Ariel, to the direct imaging attempts by giant ground-based telescopes, and finally to the detailed mapping by a future Habitable Worlds Observatory. Each step will reveal a new layer, answer old questions, and undoubtedly pose new, more fascinating ones. The investigation of this small red star and its family of fast-orbiting worlds is therefore a preview of the next century of astronomy. It is a case study in how we will come to know our galactic neighbourhood, one star system at a time, starting with the ones closest to home. The comprehensive roadmap for future observation brings us to the final and perhaps most profound layer of this entire investigation. After dissecting the star, the planets, their formation, and the tools we'll use to study them, we arrive at the underlying question that gives all this technical work its deepest resonance. What does the L98-59 system, in its totality, actually teach us about life into the universe? This isn't just about one star or 4 planets. It's about using this accessible, archetypal system as a lens to focus on the cosmic odds of biology, on the tenacity of living systems, and on our own place in a potentially crowded or terrifyingly empty cosmos. The first and most straightforward lesson is one of abundance and commonality. L98-59 demonstrates that small, rocky planets are not rare accidents around the most common stars. They form readily, often in multiples and in compact systems. This simple fact, gleaned from the statistics of thousands of exoplanets but crystallized in this one nearby example, dramatically increases the potential number of terrestrial worlds in the galaxy. If even a fraction of red dwarfs have systems like this, the galaxy could be brimming with billions of rocky planets. Furthermore, the potential water richness of Planet E suggests that the fundamental ingredient for life as we know it might be baked into the formation process of many such worlds, not delivered later by chance of impacts. This moves water from a possible rarity to a probable commonplace. So, on the statistical ledger, L98-59 leans toward optimism. It suggests the universe is proficient at manufacturing the basic hardware for habitable environments, rocky bodies with water, orbiting in zones where temperatures could permit liquid. The sheer number of opportunities for life to arise seems vast. However, the system's second lesson is one of formidable challenge. It starkly illustrates that having the ingredients and the right orbital address is only the beginning of the habitability story. The environment around a red dwarf is fraught with peril, tidal locking that creates extreme climate dichotomies, a historical barrage of sterilizing radiation, and the persistent threat of atmospheric erosion. L98-59 forces us to ask not could life exist here, but could life survive here? It introduces the concept of planetary fortitude. A planet must be more than just wet and warm. It must be a survivor with the geological and magnetic resilience to protect its volatile endowment over billions of years. This shifts the search from merely finding planets in the habitable zone to finding planets that have passed through a galactic filter of stellar adversity. Therefore, the system teaches us that habitability is a dynamic, evolving condition, not a permanent state. It is a dialogue between a planet's innate robustness and its star's violent temperament. This leads directly to the third and most humbling lesson. We have no idea which factor is more decisive. Is life so tenacious and inventive that it will inevitably emerge in any niche that offers liquid water and a chemical energy gradient, even under a locked red sun and within a global ocean? Or are the conditions required so specific, so serene, that a stable rotating planet under a quiet star like our Sun is a rare haven in a hostile universe? L98-59e is the perfect experiment to probe this. If future observations reveal it possesses a stable, water-rich atmosphere and signs of geochemical cycling, it will be powerful evidence that nature can find a way even in seemingly harsh conditions. It would suggest that life, if it gets a foothold, is incredibly resilient, and that the galaxy could be filled with hidden subsurface biospheres on tidally locked worlds. This would be a universe where life is a persistent if hidden phenomenon. Conversely, if Planet E is found to be a barren, airless rock, or a steam-shrouded hellscape despite its promising orbit and composition, it would be a sobering indication that the hurdles presented by red dwarf stars are too high for most worlds to overcome. It would suggest that our solar system's calm star and rapidly rotating planets might be a critical and perhaps less common prerequisite for complex surface life. This would narrow the most promising search parameters considerably. Thus, the ultimate teaching of L98-59 is that it holds up a mirror to our own ignorance. It crystallizes the central tension in modern astrobiology. The system doesn't give us an answer, it gives us the means to find one. It provides a real, tangible laboratory where we can test our assumptions about the universality or rarity of life-supporting conditions. Every observation of its atmospheres, every measurement of its stellar flares, is a data point in the grand calculation of life's probability. Beyond the science, the system also holds a philosophical lesson about perspective. Our Earth-centric view of a 24-hour day, a yellow sun, and separate continents may be a provincial outlier. The most common lived experience for a planet, if planets could experience, might be one of permanent day and night under a dim red sun, with a global ocean and a climate driven by hemisphere-spanning winds. If life is common, then this, the L98-59 model, might be the standard template for a living world, not our own. This challenges our imagination and our storytelling. Finally, the system teaches us about the scientific process itself. It shows how our knowledge grows, from initial detection to basic characterization to atmospheric probing to nuanced modelling of climate and evolution. It is a story of collaboration between space telescopes, ground-based observatories, theorists and modellers. It demonstrates how a single promising target can focus technological development and drive the design of future instruments. In answering the question of what L98-59 teaches us about life in the universe, the most honest answer is that it is teaching us * how to ask the question properly *. It is refining the very framework of our inquiry. It is moving us from naive optimism, there are so many planets, and simplistic pessimism, the stars are too violent, to a nuanced, evidence-based understanding of the complex interplay between stars and their planetary companions. The data we get from this system will not just describe 4 worlds, it will calibrate our expectations for thousands of others. Whether it ultimately becomes a beacon of hope for a living galaxy or a cautionary tale about cosmic hurdles, its value is immense. It is a mirror reflecting both the universe's potential for creating Earth-like environments and its capacity for forging unimaginably alien ones. In studying this small, faint star, we're ultimately seeking a context for our own existence, trying to understand if we are a cosmic commonplace, a miraculous fluke, or something in between. L98-59, quietly ticking away 35 light-years distant, is one of our clearest guides on that journey, offering not just answers, but the far greater gift of better, sharper questions.